talks that will be delivered by Bapak Wahyu Srigutomo. He is an associate professor at Physics of Earth and Systems in Institute Technology. Dr. Wahyu Srigutomo obtained his PhD from the University of Tokyo in 2002 and Master of Science from ITB in 1997, as well as the Bachelor of Science also from ITB in 1995. And in 2006, Dr. Wahyu was a visiting researcher Institute for Geothermal Science in Kyoto University. His expert is geophysical modeling and inversions, electromagnetic methods, volcanology, and geothermal. And today, Dr. Wahyu is here to share his deep understanding on modeling of hydrothermal flow in a geothermal system based on resistivity structure revealed from magnetotelluric data. Ladies and gentlemen, please welcome Dr. Wahyu.
Assalamualaikum. Selamat pagi, good morning everyone. First of all, I would like to express my sincere gratitude to the organizing committee of this conference and who invited me to take part in this event. And my simple talk is about the modeling of hydrothermal flow in the geothermal system based on resistivity structure revealed from magnetotelluric data. I'm sorry if the title is too long, but actually what I want to talk is that we propose a quantitative method of obtaining a fluid flow pattern in geothermal system. Next, yeah, this is the outline, and next, okay. Sorry if I... Okay, as I said before that this is several objectives of this study. We want to perform a quantitative hydrothermal flow modeling in our geothermal system because usually based on the geological and geochemical surface, we kind of make a fluid pattern subjectively by visual or by our experiment, for example. And we want to help the decision to make or to comprehend the hydrothermal flows by using modeling. And we utilize the modified Darcy laws, the Brinkman's equation, which compensates the effects of buoyancy force exerted on fluid due to temperature change, or we incorporated the buoyancy term. And the convection conduction equation is also simultaneously incorporated to map the fluid flow coupled with the temperature distribution. So, and of course, in this modeling, we have to know first the shape of the modeling domain, the subsurface structure based on the physical properties. For example, we can use the result from geophysical surveys, for example, from gravity surveys, from seismic, or also in this case from the so-called magnetotelluric method, which using the measured electromagnetic field variation at the surface, we want to reveal the information of this resistivity structure in the subsurface. And other physical parameters are determined from the result of geological and geochemical studies, for example, density of waters, and then the temperature of the reservoir. For example, it is obtained from the measurement or the survey of geochemistry. And we hope that the modeling scheme is complementary but important workflow to get a better understanding of hydrothermal flow pattern, which is useful for geothermal power plant development. For example, when we have to decide where to put the drill hole, for example, the production or the injection well in the power in the geothermal prospect area, maybe this result which can also helpful. Next. As we know that Indonesia is sitting on the very large expanding potential geothermal energy, it is well perceived that we have about 28,000 megawatts of potential geothermal energy, but currently we only install 4 or 5% of it in real installed geothermal plant. So, and then the government or Indonesia has taken active steps to increase investment. And the important stage also, the first one is the reliable geological, geochemical, and geophysical or 3G surveys to identify prospective geothermal system. And as we know that geothermal system is perceived to have several components. Sorry. Okay, it's weaker. For example, we have sealing cap rock or the clay cap, which is a result of hydrothermal alteration, rock that is exposed to the fluid and to the hot fluid in certain pressure condition will turn into clay mineral. And then we also have reservoir where the hot fluid resides, and also the reservoir fluid itself and the heat source, for example, the intrusive magmatic bodies from below, and also hydrological cycle, which also includes for example, the recharge area and so on. Next. And actually, as I said before, that we use the result from the 3G survey, geological, geochemical, and geophysical, to continue or to conduct our study. And I want to emphasize, but this is not my field actually, that in geochemical survey, the important objective is to estimate the temperature of fluids in the subsurface, of course, including in the reservoir, and the mixing process between magmatic origin fluids with the surface fluid, and also the possibility of the track or the trace of the heat source. And from geophysical survey, we use its ability to provide the geometry of geothermal system from physical properties distribution. Next. This is an example of how our colleagues from geochemistry and geology, of course, make a tentative model, very conceptual model of how the geothermal system behaves in terms of the temperature, reservoir temperature, and distribution of temperatures, and also the let's say the qualitative model subjectively of the fluid flow. We want to let's say contribute to this interpretation by making some quantitative modeling. Next. This is, for example, the result from geophysics. We use electromagnetics method here to infer or to obtain the resistivity structure of the subsurface. For example, this is a typical distribution of resistivity that we will have in a geothermal, beneath the geothermal area, geothermal. For example, we have this one, the conductive or low resistivity zone, which can be attributed to the presence of clay, altered clay, and the reservoir in intermediate resistivity values. And maybe also the end tip of our heat source here. So at least from geophysics we have shape or dimension of our subsurface structure. And we can also make another model from other geophysical methods, for example from gravity and others. Next. Okay, and in the end, we want to have an integrated conceptual model which correlates all the geophysical result, which constrain the shape or the dimension of the subsurface based on its physical properties, and also the temperature distribution based on the geochemical survey, geochemistry. For example, they took some samples, water sample from hot spring, cold spring, and also gas from fumaroles and others, and they analyze and interpret that. For example, this reservoir has temperature 280, for example, Celsius degree, and they combine all these results from the 3G survey into this conceptual model, including also the distribution of the pattern of fluid flow beneath the area. And the hydrothermal flow pattern is drawn visually and subjectively, and and we want to contribute or to constrain the making of this fluid flow pattern from modeling, incorporating the 3G survey itself. Next. Yeah, we propose the application of numerical fluid modeling to infer the hydrothermal flow pattern in a geothermal system, constrained by the result of 3G surveys, and the flow pattern will objectively and realistically, hopefully, enhance or even correct fluid flow pattern in the conceptual model. And the scheme is applied to several geothermal areas in Indonesia, and the resistivity section in this case are obtained from interpretation of MT or magnetotelluric data, and as well as other geological and geochemical results. Next. This is the introduction of magnetotelluric method, or MT. It is a passive method, inductive passive method, measuring the variation of natural magnetic and electric fields at the surface to obtain information on conductivity distribution in the subsurface. The source of this naturally occurring electromagnetic fields is the excitation, is the interaction between the solar plasma and Earth magnetic field for the low frequency, and the thunderstorm activity in the ionosphere for the higher frequency. This is the scheme of the field setup. We have three magnetic coil, which measure the three components of magnetic field at the surface, Hx, Hy, and Hz, and two pairs of potential electrodes to measure the electric field. This is the actual thing that we do in the field. This is the instrument, this is the coil, and this is the picture of the electrode, potential electrode. Next. Actually, in the field, we measure the variation of electric field E and the magnetic field H, and both are related by the tensor of impedance, which somehow contain information about the subsurface resistivity structure. We have 1D case, 2D case, and 3D case. It's depend on our plan or ability to interpret the data. Next. This is the example of the electromagnetic field observed in the field in time series. Yeah, we can see it's also noisy. And then, next, we invert to have more intuitive information from the data itself. We transform the data into frequency domain, and we express them into apparent resistivity and phase-off impedance, which are then next inverted numerically using some non-linear inversion scheme, for example, because the electromagnetic field problems is governed by non-linear equation, for example, Helmholtz equation, and derived from the Maxwell equation. And this is the subsurface resistivity model obtained after we invert the data. Next. Okay, this is the main part of actually that we modified the Darcy law to include the effects of temperature, and we use Brinkman equation mixed with the Bausch-Innes buoyancy term to account for the lifting force due to the thermal expansion. And the temperature distribution is obtained by the conduction-convection equation. So basically, within our modeling domain, we will have the information of temperature distribution, of course, based on our geochemistry or geothermometry analysis, and also we have to set some boundary condition in order to get the solution. And then next, in this simple study we use. I'm sorry if it looks like an advertisement. I don't get any money from COMSOL Multiphysics. Actually, we can use this one, COMSOL Multiphysics, the licensed one, of course, and also FEMLab from MATLAB, or any other UNFIS method in finite element analysis numerically. Or if you are brave enough and have time, you can make your own code, but maybe it will take 2 or 3 years to complete. So I suggest that you can. There are many commercial software, and also some, but not so many, the open source software, which is flexible enough to incorporate your differential equation problem. Next. This is the synthetic model to show you the very simple step that, for example, we from the geophysics and geological and other geochemistry survey, we have this structure. We have reservoir here, and then the low permeability altered clay, and we have fault and the surrounding host rock, volcanic overburden, and others. And then next, we incorporate or exert boundary condition. We have, for example, the surface temperature, and then the thermal insulation, and you have to set the temperature of your boundary domain here for the host rock and other. And then next, this is some the example of how we incorporate the equation, the governing equation, which is expressed in differential equation, second order, into this modeling. I'm sorry, this is too slow, too small. This is the viscosity and other permeability, temperature of reservoir, and other. Next. And this is what we have. Actually, the arrow of fluid, the color refers to the temperature distribution, and the arrow indicate or denote the fluid flow. Actually, we normalize the fluid flow just to clarify the fluid direction here. And within this modeling, for example, we have the magnitude of fluid velocity from 10 power minus 8 to 10 power minus 6 meter per second. And as maybe you already know that in typical geothermal or groundwater flow, we have magnitude or of fluid velocity for about 5 to 50 meters a year. So it's very slow actually. And then, this is the real case application of MT and TDM section in Lampung, Sumatra. We have this result from the two-dimensional inversion scheme of MT data. And then we try to next implement our scheme to this result, combined with the result from the geochemistry. And then next, this is, for example, we have heat source maybe and reservoir zone here, controlled by the presence of fault system, and we have sealing zone, caprock there. And next, this is the most important step is also to how to incorporate your boundary condition as realistic as could be. So we have to see other information, for example, secondary data, including also, for example, you follow the data of rainfall rate for a year, and then you make an average of them and make it in our influx, for example, at the surface, and then generate the model. Next, this is the example of finite element mesh use. Actually, this is it depends on your computer ability. You can make a finer one, but larger computational time and also storage. And then this is the physical parameter and from the measurement which are included in the modeling. For example, density of water, dynamic viscosity of water, specific heat capacity, permeability, temperature of heat source, temperature of reservoir, and so on. Next. Okay, this is the real one. This is the real one that we have convective cells of fluid flow in the reservoir zone, and we have also in this host rock or the surrounding rock, but its value is far smaller than the convective cell in the reservoir. And we can see also in the clay, which is highly low permeability, you don't have clear flow pattern of fluids. But if we normalize the result to have equally magnitudes of fluid flow, you will have this pattern. And this fluid pattern and thermal distribution can quantitatively help the interpretation in the next step. And next, this is Wahyu in Lampung, and this is the example case of in geothermal system in East Nusa Tenggara, eastern from Bali. We have this result from Magnetotelluric, and this is from geophysical and geochemical survey. We have many physical parameters here, and then this is the mesh, the scheme of finite element we use, and the boundary condition we incorporate, and then we have the next result. Next, this is the result. This interpretation is made before we have this one. So in this case, we can also correct or judge if the plan for the drilling is, let's say, good enough according to the model of fluid pattern and thermal temperature distribution. Next, this is the magnetotelluric resistivity section from the Slamet volcano in Central Java, and we have this next this kind of model. Of course, we can also have a dispute here whether this is a clay, for example, this low resistivity feature, or hot fluid, for example, hot fluid and which also associated with low resistivity. And then next, this is the result, for example, and the last one. Thank you. Next. This is the example from Sulawesi Agam, Sumatra, Aceh Darussalam, Nugroho Aceh Darussalam. We conducted MT measurement there and inverted the data into this resistivity distribution. And next, this is the tentative conceptual model, the cartoon actually made by the geologists and the geochemists, and they try to make some isothermal lines here, and also this cartoon of fluid flow, something like that. And we help them with our quantitative result here, whether we can help them in constraining the fluid pattern. For example, this is the result, and in hot spring we also have this kind of outpouring water here, and this is the normalized velocity picture of it. And then, okay, it's we have to the conclusion that somehow, to some extent, we managed to perform quantitative hydrothermal flow by using this Darcy law, modified Darcy law, and also simultaneously using the conductive-convective equation. And this scheme was applied to synthetic model as well as the real model from the field. And we hope that we have or we obtain better understanding of hydrothermal flow pattern, in which in turn will be very useful for geothermal power plant development plan, or contributing to the for correction of the geothermal of the conceptual model of geothermal field. Thank you very much.
Thank you very much, Dr. Wahyu. Now it is our time for Q&A sessions. If you have any questions, please.
Okay.
Yeah, Professor Bala.
Thank you very much. A very interesting presentation. Wahyu, I would like to know on the clay cap in the geothermal system.
Yes.
Is based on your experience, is there any special characteristic of clay or the indicator to make sure that there is a potential of geothermal beneath the clay cap? Yeah.
Yeah. Actually, in the field, that is the real problem of the interpretation. We have to be able to differentiate between the hydrothermally altered clay resulted from the alteration of volcanic rocks, for example, and the already there, for example, basinal plastic, the sediment, for example. But in our experience, and also from several many examples from the interpretation in the field, from the dimension we can also differentiate them, that if we have altered clay, the shape would be thinning toward the peak of the, for example, of this peak of the mountain, and it's often it makes anticline pattern, and lies between that low resistivity. We have intermediate resistivity, which, for example, from 20 to 100 ohm meters, which may reflect the presence of water in the fracture zone or high permeability, and then down beneath we have the high resistivity dome shape, something like that, which may be related to the presence of the magmatic intrusion. But the basinal clastic, which will always have a thin feature of this. Actually, that's from the shape. In our real interpretation, we have to include also the result from the thermal gradient board, for example, for 300 meters. So we can differentiate also the zone when we have enhanced of the geothermal gradient and the normal gradient, for example, like that. But other physical parameters sometimes almost the same. In terms of, for example, resistivity distribution, they have the same values of ohm meter. So that's why it's also a very important thing to focus.
Okay, thank you very much.
Other questions, please? One more question?
From student, maybe?
From student? Okay, behind. Please tell us your name and your institutions.
Thank you for the opportunity. I am Sylvia Veronica from ITS, Institute Teknologi 10 November Surabaya. I would like to ask, as we can see in the two-dimensional magnetotelluric model, you put some fault. Is that fault or log production, well production?
Okay.
Can you show the picture?
Next. Okay.
The two-dimensional magnetotelluric model.
This one. This one.
No. The first maybe? The first model?
Okay. This, okay. Okay. Okay, there, which one? This?
Book.
This one, for example?
Yeah, you can show that. Maybe.
Okay, but...
this is the synthetic model, isn't it?
Yeah, this is synthetic model. This line represents the presence of fault.
Okay.
For example, this one and this one also. And sometimes the fault system also controls the presence of the reservoir by make a boundary which characterize the location of the reservoir, for example. But you can also make if you don't have any information of fault from geological or from geophysics, you can also to omit the presence of fault actually. So in this case, for example, we try to model simple fault, the presence of faults there.
Sorry. So you mean that you put those fault only just, I want this fault like this in here, only like that?
It should be according to the result from geological result. And also from, for example, from geophysical. If you have, for example, a discontinuity of your resistivity, which makes a pattern of fault, you should consult with your geological colleague to decide whether we have to really put that so-called fault there. So it's actually in the real case, before we make the model, we have to consult or discuss many times and deeply with our colleague from the geological and the geochemistry.
Because when I see the model, there is no discontinuity or there is no anomaly resistivity in your result model. So I wondering how you put.
Which one? You have to be specific, for example. Next. This one?
Yes.
This is we, for example, you can play your model any way you like actually. But this one we put here because the geological colleagues suggest us to put it there, because from their studies they have outcrop there and there are faults, and we try to put this fault there. Actually, it's a free way in modeling, but if you have a model that is as close to the real situation, that's very good.
Thank you, sir.
Okay, thank you very much.
Thank you very much. It's very nice presentation and discussions. One more question, please. I think it's enough. It's already 10:30. Thank you very much once more time, and give your round of applause to
Thank you.
Bapak Dr. Wahyu
Thank you
Srigutomo.
very much.
And ladies and gentlemen, all we have